let's get started. Let's get rolling here. All right. Thanks so much, everyone, for joining our March meetup, Generative AI on AWS. I'm super excited for today's session. As you all know, we run those meetups every month, Chris and me. Chris says hi. He is currently attending GTC, the NVIDIA GTC conference. So I'll be hosting today's meetup. Every month, we're going to cover a couple of topics and discuss topics from our book, Generative AI on AWS. Today's topic is parameter-efficient fine-tuning that Shelbee will jump into later. And I'm also super excited to welcome a guest speaker for today, Jay Alammar. I don't think Jay needs much of an introduction, really kind of a thought leader in the space of NLP, of generative AI, works as a director at Cohere. And I'm pretty sure many of us know him from his very popular blog posts. Definitely, I've been reading that many, many times, the Illustrated Transformer and many of the others. That definitely helped me understand this pretty complex technology around transformers much better, attention mechanisms. So really, really happy that he's joining us today. Jay will be talking about advanced RAG with Cohere. So super excited for that, Jay. Thanks so much for joining us. And again, just before I hand it over to him, please use the chat. If you have any questions to Jay, we will, after his talk, do a Q&A. So we'll collect all the questions and then I'm going to have a discussion there. And then again, second talk will be PEFT by Shelbee. We're also recording the session. I mentioned it in the chat. Recording will be posted to our YouTube channel. And with that, Jay, no further ado, I'll hand it over to you. Let me stop my share.
Amazing. Thank you so much for the kind intro. It's great to be here with everybody speaking about some of the most fascinating topics out there. I'm really fascinated about language models and what they do, and retrieval-augmented generation is one of these use cases that are probably the highest sought after use case in enterprise. Just take a step back. I used to go around giving these talks 2-3 years ago and had to sort of explain to people why language models are amazing. And you can set it into a historical context by seeing that technology changes every 10-15 years, and that creates new opportunities, new kinds of companies that are possible, new types of industries. They change sort of what's possible. In language technology in general, in the past has had major jumps. So if you think about the invention of writing, for example, that's what we actually call the beginning of history. And that is just a development in language technology. The printing press is another one. If you needed a book before the printing press, you had needed to sort of go and copy it yourself or pay somebody to go copy it by hand. So books were expensive, literacy rates were low, but then after its invention, sort of people started being able to afford books and literacy sort of grew, and then we have the science and technology revolution sort of coming after it. And so this is like a necessary context for saying, we're at a jump in language technology, the magnitude of which we don't really understand yet, but it's showing incredible promise and potential that can possibly be on par with these previous sort of jumps in language technology. We basically have software that can speak back. We've made objects sort of speak, and that's magical in its sort of own way. I've been following the topic for a long time. I've been blogging about machine learning and language models for close to 10 years on my blog. The Illustrated Transformer, as was mentioned in the kind intro, is a source for people to sort of learn how these models work. It's been read by maybe 3 million people so far. I am co-writing a book with Martin Grotendorst on language models called Hands-on Large Language Models for O'Reilly. You can access it right now. In early release, you can access the first maybe 5 or 6 chapters. It's coming out maybe August. It's going to be about 350 pages. but it has hundreds upon hundreds of figures that explain so many different applications of large language models and how software developers can come in and use them to solve problems. So the transformer, the T in GPT was this massive jump in the abilities of deep learning that is powering a lot of what AI is able to do now. And a lot of that came out of this transformer paper, Attention is All You Need. One of the co-authors is Aidan Gomez, who's one of the three co-founders with Nick and Ivan, who founded Cohere, which is the company where I work, where I've been for 3 years. And Cohere trains large language models of multiple types to solve business problems. And the focus there is to empower developers, but and a lot of the focus is also on large companies and enterprises on how to solve problems and how to use language models for practical applications. And I really joined Cohere to see how this technology sort of goes out from the lab into application, into industry, and how it becomes sort of features and product. And that's a lot of what we're going to be sharing with you here today. So you're in the right place if you're thinking about how to learn or how to build LLM type products. Now is absolutely the right time to be building because the potential is very clear of how much change these models are going to be able to do. There's so much room for creativity and sort of rethinking existing problems and building solutions that were really never possible in software before, especially tackling language and maybe generation of audio and video and images. So when I would go to some of these talks 2-3 years ago, I'd have to explain to people what language models are and why they're interesting and they're fascinating. I don't need to do that anymore. People already have interacted with a generative chat of a system of some kind. So the awareness we try to raise now is to say, okay, so you've interacted with one of these models, but it's good to have a more useful perspective to hold about these models, not to think of them as these digital brains that just take text in and text and return text out. So that's the first, let's say, impression that a lot of people would take. So the advice is actually to think of them as capabilities, as tools in your toolbox, as a builder, as a developer, as an entrepreneur or a founder, or a business leader to sort of problem solve with. That is a more useful perspective to have than just thinking of them as this black box digital brain. And when you think about language models and language AI in general, you can say that there are these language understanding capabilities. That is one family of capabilities that the language models empower. And then there are language generation capabilities. And these are, let's say, two general families. Now, if you've seen image generation models, DALL-E or Sora or any of these, or Midjourney, even though they're image generation models, they do employ a language model for the understanding. So there is a part that it's the part of the system that takes in your prompt and sort of understands it in a way and sends it to this other component that generates what you want. And so language models are enabling prompt as a user interface. So even if they're not generating text, they can be used for understanding. And that's, let's say, one important example of how these systems can be used. But then generation is the application that gets the most focus. It's the unfortunate name being called now is generative AI. And I will mention in a second why it's a little bit unfortunate, but generation or language or text generation is also multiple subcategories. So where generative chat is only one of them. But then you have things like summarization. Summarization can be done really well with these models. And so it's a generative application. Copywriting, if you tell the model to sort of write you an essay or an email about something, that is an application or a generation capability that you can use in a pipeline. And there are a few others that are language generation capabilities. Now, why I say the label of generative AI is unfortunate is because a lot of the most powerful and robust and reliable use cases of AI that also grew dramatically the last few years are not generative in nature. And these are a lot of these are on the understanding side, but they're also on the search side and classification. So we'll talk a little bit about semantic search, or this is the idea of using language models for search, which is vastly underestimated, and it just really improves these systems that you can build. And having a good grasp of these types of systems is very important in your sort of vocabulary of how to build with language models, where we'll be covering some of the main intuitions here, and then seeing how they coalesce into this major application of retrieval-augmented generation, or RAG. Text classification is another one. This is where your software systems can be a little bit more intelligent. So, if they get an email or a message, they can say, okay, this is for marketing or this is for sales. So you can build a little bit of that intelligence into your systems, and language models empower these capabilities. So semantic search is this idea of search by meaning. And it's one of the most reliable and robust use cases that you can use language models for. Now, when we say search, we're not saying that you're definitely going to be building the next Google search. So this is not about for people who are just building web search products. Search is one of the most important features in any applications. Every company needs to search its internal documentation. There aren't, let's say, dominant solutions that cannot be improved further for internal search. Every application that you, for example, interact with, every app on your phone has a search functionality, or most of them at the very least. And not a lot of them are at the highest sort of quality, and a lot of search can be improved. So search is a major component of software systems. And so knowing how language models improve this and take it to the next level is an important thing to have in your toolbox, and language models empower that. So let's think about a query. So let's say you want to travel for a business conference or something, and you're in Brazil, and you want to search for Brazil to USA, and maybe the policies of your company for stuff like that. Now, if you use a naive keyword search system, which is the systems before language models for search, it might get you this result: USA to Brazil. So it just flips USA and Brazil, because the query and this document have the exact same keywords, but the order here got shifted, and that shifting sort of changes the meaning dramatically. And a naive keyword search system might sort of not pay attention to that. But searching with semantic search is able to capture, language models for search are able to capture more of the context and the intent of the search and the query, and they're able to sort of return better results. Semantic search has many different kinds. The two sort of most important ones, or categories or families, are these. One is called dense retrieval, or search by embeddings. The other one is called reranking. Dense retrieval or search by embeddings kind of look like this. If you've used Weaviate or Pinecone or Chroma or Quadrant, like this is the concept that is used in these vector databases, where you have a query, it's passed to a vector database, and the vector database has access to a text archive, and it gives you the results. Let's say it gives you the top 3 results. What happens on the back end is that the search query is actually sent to a language model. And this is an embedding language model. This is a model that takes in text and outputs not text. It outputs something different. It outputs a vector, or a list of numbers that capture the meaning of that query. And then that vector is passed to the vector search database, which finds the nearest neighbors for this vector. And the nearest neighbors will turn out to be the best results for this search. And these embedding models are not, let's say, naive embedding models trained specifically on text similarity. These, for semantic search, they're optimized specifically, and they have a training period, let's say, or the majority of their training is for questions and answers, or for queries and results. So they're optimized for this use case. really love using there are the concept of embeddings is so powerful, and you can use it for semantic search, but I also love these use cases of just using it for exploration. So let's say embeddings can allow you to read 1 million documents at a glance and sort of get some of the most important information out of there. So let's say you have 1 million tweets to a customer service account or something. You can embed all of them, get a vector for each one of these tweets or messages. Then you can plot them, you can cluster them, apply clustering, and sort of this tells you information very quickly. And so you can tell that, okay, 40% of the messages that this, let's say, company got are about returns or about this topic or that topic. And I really love like using also the generative models to apply labels to these topics. These are fascinating and powerful sort of tools where you're chaining embeddings and generation now, kind of like what we'll see in retrieval-augmented generation. On the Cohere side, we a couple of months ago we launched Embed v3. It's a multilingual embeddings model. Works on over 100 languages, super high performance, but it's specifically optimized for RAG, where if you give it a query, so some of the failure points of RAG systems is when the retriever sort of doesn't give you the right results. And this embedding system is not optimized just for search, but also specifically for retrieval-augmented generation search, where if you give it a query kind of like this, COVID-19 symptoms, it will favor documents that actually have a description of those symptoms, not documents that are just similar to the query in its meaning, which can be a document that says COVID-19 has many symptoms. That's not useful for a RAG system. And so that RAG optimization is one of the first things that you get out of Embed v3. Our team have embedded all of Wikipedia in 300 languages and released that for free for you to download. And you can find that on Hugging Face on this URL. So you can get all of Wikipedia, about 250 million embedding vectors, and you can build just incredible things that ground on the world's information as stored in Wikipedia and ready for you to just download, plug it into a vector database, and just build something incredible with. So this is an exciting release, and we're sort of really excited to see what people build with. So you can just go to the Hugging Face page of Cohere, and you'll find it. Now that covers embeddings, or the idea of dense retrieval. Let's talk about this other method of semantic search called reranking. And reranking is the fastest way to inject the intelligence of a large language model into a search system. So a lot of people, want to get AI products out there or an AI feature. This is the fastest one to get out, and sort of it gets immediate results, and it improves an existing search system without sort of changing a lot. Reranking works in this way. So you have an existing search system. It doesn't have to be an embeddings model. It can use embeddings, it can use Elastic or keyword search or open search or a hybrid. And when you get a query, you send it to your existing search system, and that gets the top 100 results. And then you just apply one API call to this rerank endpoint on the Cohere side, and you give it these 100 results on the query, and it just changes the order. And it says, okay, this document that you listed as number 33 is actually the most relevant for this query. And so I'm going to put it at number 1. And this document that you placed as number 12 is actually the second one. So I'll put it at number 2. So this is just one API call, changes the order of the top 100 results, and just dramatically improves any existing search system. Basically, how it works is kind of like this. So if you're aware of models like Barth and the idea of crossing coders, that's how the model works. So you basically present to the language model, this is a specific re-ranking language model that works like this, in this crossing coder fashion, where it gets the query, it gets each document, and assigns a relevance score to each document. And then when you sort using these relevance scores, you get the new rankings. You can see the sort of immediate uplift in any kind of system you apply a re-ranker to. And so whether you're starting out with a lexical search like Elastic, or you're using top of the line embeddings models, adding a re-ranker step is a natural way to sort of improve these systems. And this is especially important for retrieval augmented generation, where you get, if the relevant document in the context is not in the results that you pass to the generation step, your RAG system will not function as you like. And so every improvement that you can sort of improve on the retrieval side is vastly important. So re-rankers are, you know, some of the best ways to improve these systems. And so here you have these two ideas of the embeddings, model or endpoint, and the re-ranker, and they're both sort of available on AWS SageMaker at the moment. So this has been, let's say, a look at language models for search or understanding or representation. But this is also, if you're specifically interested in generation, these are some of the most ideas in text generation. Because think about these two questions that you ask a model, and this is one of the first realizations when sort of large language models exploded in popularity, and people started asking them factual questions, and they sort of very quickly realized that, you know, this is not their strongest suit. People started labeling this idea as hallucinations. And so and this is something that people in NLP have always, you know, known and warned people that, you know, don't use these models for factual. They're trained on generating language that is, let's say, coherent or understandable, but they're not specifically originally trained for search. And so one of the first solutions that are, let's say, rising to enable models to function better when answering questions factually is to say, you know, instead of giving a generation model a question, maybe you give it the question and some context, and that context hopefully contains the answer, and then that it will improve the possibility that model answers correctly. And so this is where we sort of started shifting the input into the model from a question into a context and a question. And here you get a bunch of different benefits. So the information that you're relying on is not the information that is stored inside the model that it sort of got from its training process. You are now augmenting this model with another data source where the world information is no longer sort of stored in the model. And you get so many benefits from this kind of thing, where you can update the information, for example, without having to train the model for another 8 or 6 months until sort of it encodes that information. And it enables you to have smaller models that are sort of specifically geared for this use case, and that leads to cheaper models, easier to deploy, faster latency. And so once you see this idea that of retrieval augmented generation and augmenting the information with a data source of the model, it becomes like a no-brainer. It also enables you to, let's say, up-to-date information is an important one, because information in the real world changes a lot, and you want the model to have the latest data. And you can also build systems where user A has access to this database and user B has access to other, let's say, data sources. So these become tools in your additional tools in your toolbox as you sort of get into these systems. And if you build in tools like citations, your RAG system sort of is a little bit more transparent to the user. And it says, I give you this answer by looking at these documents, and these are my sources, and these are my citations. So you don't have to rely on the model's word. You can sort of double check it, which is something we've usually done when we cared about the source of information. So if you use Wikipedia or something, you have the citations, you can go and check out the resources and learn more and sort of make up your own decision. So citations are an important thing that you get. And so this is the concept of retrieval augmented generation. It is the intersection of generation and semantic search. And one other way to look at it is that now you have a data source that is linked to your language model, where your language model is able to consult it. And so you're able to ground your language model into this data source. So you can chat with a language model about your company data, about your ERP, about your customers, about your CRM, about the documentation of a tool that you're sort of trying to build. And so now this conversation with this generation process has two steps, a retrieval step and then a generation step, instead of just asking the model directly. And so one way to do this with semantic search is to say, okay, you search for it. When you get a query, you send it to your search system, which can be empowered by embeddings. It doesn't have to be. And then you get the top result. And then that's, let's say, top 1 to 3 to 5 results. These are the new context that you put into a prompt, and then that prompt you send to the language model. You can, again, improve that by adding a re-ranker step after that search. So you have the model give your system a better chance of getting the right context to the model. And then now your system kind of looks like this, where you have the retrieval and generation. Now you have 3 language models, where you have the embeddings and re-ranking language models on the retriever and the search side, and you have the generation model sort of doing the grounded generation. Now, the challenge, if you've built a RAG system, the challenge is that in the demos or tutorials, you see simple questions where they're very precise and their answer can be sort of in one word. But then when you deploy something to the real world and you find that your users are actually asking questions like this, and they say, we have an essay due tomorrow. We have to write about some animal. I love penguins. I could write about them, but I could also write about dolphins. Are they animals? Maybe. Let's do dolphins. Where do they live, for example? Now, does it make sense for you to take all of this and give it to a search, throw this at a search system and say, give me the best results for this entire thing? If you come at it and view it this closely, you can find that there's probably a better way of doing the search, because the search part of RAG systems is where most of the failures sort of exist. So if you ask this to Coral, which is Cohere's agent, you can try this on coral.cohere.com. It will give you a UI kind of like this, where it gets your question and it says, to answer your question, I'm going to search for this. And so there was a translation here to the search system that says, when I need to get the information that I need to answer this question, this is the query. I don't send the entire thing A. No, I send B. That's how I find the solution. That's something that language models can be trained to sort of do. And it's an area where Cohere's models are specifically optimized to do. And then, so now this is a step called query rewriting, where you rewrite the query that you send to your retriever. And code.chat is Cohere's endpoint that sort of can give you this capability where you can say, give me these search queries to answer this. And it actually, it's beautiful in that it gives you 3 options, or 3 types of options. So if somebody asks your RAG system to say, or somebody says hi or hello to your RAG system, you don't want that hi or hello to be sent to a database and results. You don't need a grounded generation to hi or hello, or a greeting that the model can sort of answer simply by its own. And so the query rewriter has to say, I need to search or I do not need to search to answer this question. And then that's a one capability that you get, let's say, out of the box here, out of CodeChat. But then there's another class of problems. Let's say you have a question like this. So compare the financial, let's say compare the financial results, let's say, of NVIDIA in 2020 and 2023. Now, do you want one document that compares these 2 things? You might not find a document kind of like this, but then you might be better served by having 2 search queries. So not just 1, but 2, and then you give these 2 contexts to the model, and the model sort of, and so this is the idea called multi-query RAG systems. And this is another thing that you get out of code.chat here. And so that this splits off the question into multiple search queries. And then finally, this idea of citations is also an important one, where you can, with CodeChat, you can give it the context or the results, and it will say, generate a result, and it will say, okay, these two words, their source is this document, and then these two words, their source is this document, and so on. Now, this is something you might have seen in some applications or in some search. But the thing that is a little bit different on the Cohere side is that we're doing this as an API for you to build products like this. So we're not, let's say, even though you can find this easily in Coral. So this is Coral, for example, and I can, let's say, ask it to tell me about the book Generative AI on AWS, for example. And where it says grounding, you see, now this is where it's telling you what it's searching for. And it's grounded by web search. And so it gives you the information, and these are the resources or the citations. So this is where it got the names of the authors, the goal of the book, and these are different sources from sort of different places on the internet. You might have also seen this in, their entire tools that are built on this, and this is just one API call, kind of like this, that you can build into your products. Just last week, we released Command R, which is sort of our model that is specifically optimized for retrieval augmented generation with all of these sort of capabilities. We also released the weights, so you can also download the weights for research purposes and play around with this model. It's the top trending model on, last I've checked this morning, on Hugging Face, and you can see how people sort of favor it in retrieval augmented generation use cases and in RAG evaluations. Developers have been loving it, calling it the undisputed RAG king, crushes citations, fast as hell, follows commands perfectly. We're really excited about people's sort of feedback on Command R, and I hope you get to sort of play around with it. And so with this, now you have an understanding of this pipeline of retrieval augmented generation, where you have a retrieval step, and that step is empowered by an embeddings model, a reranker, and a generation model to do the query rewriting. And then you have a generation step that is empowered by this language model that does the grounded generation. And then you also get citations on top of that. The top thing when we talk with large companies and enterprises is their focus on their data security and data privacy. And so that's an area where just working very closely with AWS on SageMaker and Bedrock. So we work with Cohere's, let's say, cloud agnostic. So you can find Cohere on every cloud, but we have on the AWS side, there's, let's say, multiple different kinds of private deployments where SageMaker and Bedrock, you can find the models there, but you can also do these private deployments on your VPC. There's this guide here on how to build something like this, a chatbot like this. This is the UI. It's a highly visual examination of how to do this, containing the code where you can build a system that does all the steps that we talked about: embeddings, re-ranking, query rewriting, with even multi-query rewriting, and citations. And we have a notebook there that sort of guides you through all of that. And so if I'm to leave you with one concept at the end, it is this awareness of, think about these models as a collection of capabilities that are tools for you to build pipelines with, where you can have multiple steps instead of thinking of them as this giant tool. And then the importance of, let's say, retrieval augmented generation, and how you can improve it, and how you can sort of take your RAG system to the next level with re-ranking, with query rewriting, and with citations. We have information like this and a lot more on llm.university. So I got to collaborate on this incredible Cohere project with some of the best ML machine learning educators out there, Luis Serrano and Mior Amer, are some of the best communicators of large language models concepts I've ever seen. And there's so much content here that is highly accessible, free for you to access. You don't need to sign up. Just go and learn. And there are videos and lessons and code examples. So definitely check out llm.university. And with that, thank you so much for bearing with me.
Thanks so much, Jay. Awesome presentation. We got a ton of questions here in the chat. People have a lot of questions. I think and a ton of them around the re-ranking actually that you presented. I think there's more educational content around that if folks want to check that out on the LLM University as well, right?
Yes, absolutely.
Yeah. So let me just pick a couple of those questions here in the interest of time that I think a lot of people are interested. So one question, we see LLMs coming out with larger and larger context windows, right? That size just keeps increasing, it seems. So what is your take on having those large context windows? Will they replace RAG? Will there be new techniques that kind of, makes intelligent use of it? Or how do you see larger context windows in relation to RAG?
Yeah. So I would say RAG is here to stay. It's not definitely going to be the only one. So if you have, what are you grounding against? Are you grounding against a document or a book, for example, that does not change? That you can probably fit into the context. If you're grounding against the customer service messages that we got that are stored in the database, new messages come in and come out, are you going to query the database for all of that text every time you want to ask a question and send all of that to the language model? That is not, let's say, the proper way to do every use case. And then there are a lot of times where you want to ground on massive amounts of data where no model sort of is able to fits, let's say, Wikipedia entirely into its context. And then if it can fit it, is it the right thing from a cost and, let's say, latency? Does it make sense for you to have a language model reprocess 1 million tokens every time you want to ask a question about it? There are so many different sort of aspects to that. So I would think due to first, that information changes, and if you're grounding on a database or in your Slack, it's not, let's say, the best engineering approach to take all of your Slack dump and throw it at the language model every time you want to ask a question. So there definitely smaller use cases that can be solved with long context, but I absolutely believe RAG is here to stay.
Perfect. Another question, the Cohere embedding model recommends requesting to embed 512 tokens for optimal quality. And one token is, I think, around 4 characters on average, right? Do you have any numbers, question here, around the loss of accuracy with a less or greater number of tokens?
So
is there any guidance?
Yeah, this is one of the biggest questions where people sort of who will if you want to embed things, you need to break down the text into chunks. And so what is the right way of doing chunking? And really depends on the use case. But when I asked our head of embeddings, Niels Reimer's legend, who created sentence transformers, the guidance that I get from him is ideally, you need to encode one idea in one vector. And so that is how the language model is able to sort of retrieve the answer. Now, the appropriate chunking really depends on your use case and how much of the context is required for the specific use case. But very long context windows, you're doing too much compression. You're having one small vector contain so much information that is not sort of giving the search system the granularity that it needs to sort of zoom in on specific information needs when people need this one piece of information and not that one. And so the general tendency is to say one idea, one concept. So maybe a couple of sentences or a paragraph is a good default, but then try it on your use case and sort of go from there.
Got it. Yeah, and there's a ton of questions here, RAG versus fine-tuning, right? And in general, how do I keep my workflow, my models updated with new information coming in, right? We had a couple of questions around the embedding model, is there is there any issue if the embedding model isn't updated, right? Like with new information as well. Like in this whole, I guess, reg end-to-end workflow, what's the best way to handle this, right? And
yeah, fine tuning is another important tool in your toolbox, and it's something sort of that Cohere supports. But I would say there's a little bit of a difference or a nuance of why you want to fine tune. So you want to fine tune, for example, to have the model, zoom in on a specific behavior. You want it, for example, to always output things in this one format that you're not able to get from few shot prompting. You have a very specific, I don't know, kind of XML that you want the model to sort of do, and you don't want to maybe put all of these examples in the prompt. You want to save some tokens. You can fine tune a model to output specific sort of format or specific behavior. That's one area. The other area is you fine tune a model to give it some understanding of the context that you're in. This is domain adaptation, where it's like, okay, this is a generalist model, but we have a very specific legal domain where the model needs to understand that this words mean that and this words mean that. That's another sort of great use case for fine tuning. But fine tuning to inject the model with general sort of information about a field is not necessarily the first thing that people would go do fine tuning, because it's expensive. You don't, let's say, get the guarantee. So if you're able to fit the information that you need in the RAG context, in the prompt, that is maybe the first thing to try, and then fine tuning you revert to in sort of these other sort of the use cases.
nice. And let's do one last question, a little bit more looking into the future. We always love that. There's a lot of hype around on-device LLMs like Edge, right? LLMs on the edge this year. What is possible now, and what would make on-device the natural choice? Like, what are the typical use cases, right? And maybe where do you see this space specifically evolving?
Yeah, so it's exciting to see smaller and smaller language models being more and more sort of capable, and that's going to continue. We will need to continue to shrink them and sort of have them super specialized in these use cases, and the hardware sort of needs to catch up. It'll take time. Maybe self-driving, maybe let's say autonomous features of cars is the edge where there's the most capability. It'll come to your phones, but maybe at a later sort of step, because just the power requirements and the computation needed it's getting there. You're starting to see features pop up bit by bit. Some of them hit a server and come back, but some of them are doing it locally. So it's definitely gonna continue to improve on, but you'll continue to see this pendulum that always happens. Do we do it on local computers? Do we do it on the mainframe? Do we do it locally on the cloud? It's this constant sort of swing.
Right. Perfect. All right. Thanks so much, Jay. It's been amazing. Thanks for joining us today and sharing your insights. We will share the recording with everyone, just to quickly call it out here. So we'll post that to our YouTube channel. And I know we didn't get to every single question here in the chat, but I think there's a lot of excitement, which is really great. So check out the resources that Jay shared, LLM.university. And also there were a ton of questions on Cohere on AWS. I posted a link to the site. Cohere models are available both with SageMaker, with Amazon Bedrock. So make sure to check out those resources if you're interested in that. And yeah, with that, thanks so much, Jay, for joining us today. It's been a pleasure.
Thank you. Thank you so much for hosting me. And had a blast.
And I'm handing over to Shelbee. So in the remaining time today, Shelbee will dive into one of our book chapters on parameter efficient fine tuning. So it's a great segue from our discussion, right? When should we do reg? When do we fine tune? So let's talk a little bit about how I can fine tune efficiently. Shelbee.
Perfect. Thank you. And thank you so much, Jay. Great presentation. Let me go ahead and share my screen. All right. Hopefully everyone can start to see my screen soon.
Yes, we can see it.
All right. Perfect. So yeah, so Jay talked about, so typically when we see kind of the progression of a use case, right? Is starting with that, business objective, the use case you're trying to solve for. And then the most common kind of progression in customizing models we see is, first doing some prompt engineering. If that doesn't work, if you need more domain specific knowledge, especially more dynamic domain specific knowledge or data, moving on to RAG, right? So Jay went through RAG beautifully and went through some of the, even some more advanced topics within RAG. And then, in terms of then moving on into fine tuning, we see that often with data that is more domain specific, but also like relatively static too, right? Because with some of those RAG based architectures, you can also, as you can imagine with the different hops, there's some latency that's involved in like going to a vector store, then going to the generative model, all the different steps and kind of post processing of that RAG workflow. But in the case where there is like relatively static, domain specific data, sometimes fine tuning does make sense. And the techniques don't operate in isolation either, which I would call out, where it is possible where in a one use case, one solution, you have a fine-tuned model, you're also doing RAG-based workflows. So it's definitely possible to, combine some of the techniques that we're talking about. So if we look here, so in this chapter, so PEFT is actually chapter 6. We do also talk PEFT. We talk about PEFT again in the multimodal chapters of 10 and 11 as well. So like applying parameter efficient fine-tuning methods to multimodal models as well. But in the context here, we start out with PEFT specific for large language models as a parameter efficient form of fine-tuning. So with PEFT in comparison to full fine-tuning. So with full fine-tuning, you're actually basically updating the weights of that base foundation model, right? So you're actually using a base foundation model, doing full fine-tuning, updating the weights of that model. And that can be a fairly heavy process in terms of compute and memory, depending, right? There are methods where you can, make it a little bit less. But the most common method that we see here is parameter efficient fine-tuning and being able to still perform fine-tuning, but doing it in a parameter efficient way, meaning you're able to largely freeze most, if not all, of the weights of the original foundation model, and then train a set of adapter weights on top of that. So by doing that, you're able to train less parameters, which requires less CPU, less memory, and that sort of thing. So within the chapter, we talk about a few different techniques. There is a really good research paper out there. I think it was in like May of 2023. There is a reference to it in our book as well, but a really good research paper that goes over some of the techniques and the various techniques and kind of the categories they fit within parameter efficient fine-tuning, as well as some of the effectiveness of each methods, because some methods are more impacting to things like accuracy, performance than others. So what we tried to do is we focus quite a bit on one specific method. We do go into a few others too, but we do focus quite a bit on LoRa, which is a really common technique. So let me go through, I'm going to go through LoRa. I'm going to talk a little bit more about parameter efficient fine-tuning just in general, but with parameter efficient fine-tuning, you can see here, like I talked about, the base weights of the foundation model are largely kept frozen. You're basically tuning or training a set of adapter weights on top of that. And the benefit with that too is you can see if you're doing full fine-tuning for a specific task, you have the end result is a brand new model artifact, right? So it's a brand new model artifact, large in size, takes a lot to host that, and also tune it for performance during inference, so different optimizations. In the case of parameter efficient fine-tuning, instead of hosting that large foundation model kind of over and over again, in theory, theoretically, you can actually train these PEFT adapter weights and swap those out at inference time. How effective that is in terms of latency, there's some startups in the space coming up with really cool solutions in being able to swap out those adapters at runtime. The other alternative is you essentially move that PEFT or merge that PEFT adapter with the larger foundation model and host it. But either way, you're still able to reduce the amount of compute and memory that you're using during your fine-tuning activities. So like I mentioned, we focus quite a bit on LoRa and QLoRa. So with LoRa, it's a really common parameter efficient fine-tuning technique because it is really effective, lighter weight than full fine-tuning, and it has minimal impact on performance and accuracy, right? In terms of like inference in evaluating that model. So if we look at LoRa, so LoRa is basically using a set of lower rank matrices, right? So you're actually keeping the base weights of that foundation model frozen, and then you're training a set of adapter weights using these low rank matrices. And the reason those matrices are more parameter efficient, you'll see if we look at an example here. In a typical full fine-tuning example, if we're using the dimensions of like the typical transformer weights 512 by 64, you basically have 32,768 trainable parameters. It's a lot of parameters to train, right? You're updating all of those weights in full fine-tuning. In comparison, when you're using parameter efficient fine-tuning, you're training these lower rank matrices, right? And you set the rank as part of your fine-tuning activities. And this example here is just showing training, 64 by 64. So what this ends up, sorry, it's actually supposed to be 512 by 64. This is an old copy. The newer release has the 512 by 64 in it. But what that ends up with is 2,304 trainable parameters. So you can see you're training a lot fewer parameters than that 32,000 roughly that we saw before. As a result, you're using much less compute, much less memory to be able to fine tune for your tasks. So it ends up being extremely efficient in terms of being able to fine tune for your domain specific tasks.
And Shelbee, just real quick, sorry, could you zoom in maybe a little bit?
Oh, yes. So sorry.
Yeah, so we can see the graphic there better. Yeah.
Is that much better?
Yeah, thank you.
So sorry. That was probably an eyesore for everybody for a good 5 minutes now. So hopefully that's better. So in general, so if we look at applying LoRa, this is just some code. There is a GitHub repository that I know you guys have probably seen several times that actually has some examples, some real life code examples in being able to apply LoRa, utilize LoRa for fine tuning. But if we look at it from this perspective here, right, you have these low rank matrices that end up getting trained. So we call these adapter layers quite often. And what ends up happening is these adapter layers essentially get added with the original frozen weights, which is much less invasive, obviously, than changing that original frozen foundation model. And like I mentioned before, there's different ways in terms of inference with these adapter layers. So, sorry, it's not going very smoothly in this. Yeah, so there's different ways to do it at inference time, right? With the adapter layers, which are much smaller than that the fully trained foundation model. You can either merge those adapter layers at runtime. So you merge it with the base foundation model, it ends up becoming one model artifact that you then host and perform inference on. The other option, like I mentioned before, which is where some of like that key benefit comes in, is the adapter layers and actually swapping them out at runtime. So that in theory, essentially you're hosting that larger base foundation model once. And then the adapter layers, which are much smaller, as we saw, you're able to swap that out at runtime depending on your task, depending on your use case. And there are some pros and cons to each approach, right? So if you're merging it, as you can imagine, you don't have kind of that swap or that merge at runtime, right? So it can be lower latency. The kind of con of that is that you then are essentially storing the base foundation model with the adapter weights and loading that up and merging that and setting that or hosting that model for inference. And this is going into the maintaining the separate LoRa adapter. So this is in the case before we merge the model, we're hosting that as essentially a single model artifact serving model. In this case, instead, you're hosting a foundation model and then maintaining those LoRa adapters separately, swapping those out at runtime. That swap out can have some increased latency with it though. So those are some things to kind of consider on whether you merge or you maintain separate LoRa adapters. And this one, we're just kind of going into, sorry, Adobe is not enjoying me today. These are just some metrics on full fine tuning versus LoRa performance. So you can kind of see here, there's almost no downside, right, to actually using parameter efficient fine tuning, specifically LoRa, to do your fine tuning for your domain adaptation. And you'll see here the difference between full fine tuning versus LoRa based fine tuning is very minimal. So as long as you can have, even if it's a super small accuracy hit, LoRa fine-tuning is extremely effective to do. Q-LoRa, we go into this a little bit. Q-LoRa is essentially LoRa, but it's quantized, right? So it's actually using 4-bit quantization. So going to an even smaller representation of that model to train out those adapter weights. So we do focus quite a bit, like I mentioned, on LoRa, Q-LoRa. There's a lot of examples in the GitHub repo as well. We do also talk about a couple of other methods, prompt tuning and soft prompts. So with prompt tuning and specifically with soft prompts, essentially what we're doing is not fine-tuning the model. Once again, that model stays frozen, but we're essentially training the prompts, right? By creating soft prompts right next to the hard prompts. The hard prompts are that actual prompt that you enter in natural language. The idea of these soft prompts is that these are trainable tokens that actually are used and sent along inside with the hard prompts into your generative model to then guide that model to a more targeted answer, essentially, right? So another way to customize the model. In practice, I would say I see like LoRa by far the most. Not sure about others, or if Antje, if you have a perspective there, but I would say by far I see LoRa-based fine-tuning as probably the most common parameter efficient fine-tuning right now anyway. I'm sure other methods are going to come out that'll then expand that. So then we just kind of go into the summary. And like I mentioned before, we do actually cover parameter efficient fine-tuning in the context of multimodal models as well in the later chapters of 10 and 11. So we have 10 and 11 here, but you'll notice we do actually within the multimodal chapter cover how to actually apply parameter efficient fine-tuning techniques to multimodals as well. So we have an example of that inside there as well. So I went through a lot. I don't know if there's any questions built up in the chat. I know we are closing up on time. Let me check the chat.
Yes, thanks so much, Shelbee. So we do have a couple of questions here coming in. Let me just see. We had a couple of questions like on the effort, the merge of the, the big W matrix and the delta with the LoRa adapter. Is that a simple operation? Like how heavy is that?
I would say it's simple with thanks to like Hugging Face and other tooling libraries that allow us to do that merge and load for us. So you'll notice inside the book, we do, or not inside the book, actually coding examples, we do use merge and load, right, from Hugging Face. So I think because of the advancements in tooling, some of that lift that would have been required before, we're able to do that a little bit better with some of the advanced libraries that are out there.
Right. And we do have questions here around, the quantization that's used, right, in those methods. So somebody asked about any experience with binary quantization that goes down to 1 bit, Q-LoRa, which uses quantization at the time of fine-tuning. How does that affect accuracy of the model?
Yeah, there's always a potential to impact accuracy, right, whenever you're doing quantization. So it's one of those things which is the worst answer on earth, is you really kind of have to test it for your use case, right, and see if the going down to that level of quantization impacts the results that you're getting. It's the worst answer, which is it depends. But yeah, there is going to be a hit, right? It's just how big that hit's going to be.
There is no free lunch, basically.
Yeah. And can you tolerate it, right? For your, and maybe you
Right.
can't tolerate it, which is fine.
Right. But we've seen like, empirically from use cases that, especially compared to full fine-tuning, right? Depending on the use cases and of course, like which SLAs you have for your specific implementation. But usually the benefits are outweighing the loss in accuracy there.
Yeah, because there could be such a minimal hit that it's not really that huge of an impact.
Yeah. Questions around the data, I think, how much data is required with LoRa, and then maybe wrap it up in general recommendations on how to manage data sets for fine-tuning.
Yeah, and like in terms of how much data is required, it depends. Like if you look at Bedrock fine-tuning, right, as one example, I think the number we give there is anywhere from like 500 to 1,000 examples that you should be able to fine-tune with. It depends, right? Once again, so you can get away with relatively low number of examples, but I would say I mean, the more examples you have, as long as they're quality examples, the quality of that data that you're using is probably even more important than the quantity. But yeah.
Perfect. All right, we have to wrap it up here. We're on time, but thanks so much. I posted a bunch of links here in the chat as well. We'll post the recording to our YouTube channel, links in the chat. And thanks so much again to our speakers. Thanks so much, Jay, for joining us. And thanks, Shelbee. And hope to see everyone in our next month meetup.
Thank you.
Thank you. Bye-bye.